Hey everybody, welcome to another math video. Welcome rock stars. Today we're going to talk about irrational numbers, both positive and negative radicals. I'm going to dive into a pretty challenging topic, which reminds me of, the old story about what do you get when you cross a football player with an elephant? You get a runner that nobody can tackle because it's an elephant. Get it? Oh, I thought I was in a concert. Let's go. Today we're going to talk about your target, which is you're going to be able to compare and order and locate irrational numbers on a number line. And then you're going to be able to use radicals that are both positive and negative from 0 to 400. Let's roll. Okay, so vocabulary right off the bat. Irrational numbers. If you have not done any work with irrational numbers, this may be new to you. I have a video on rational numbers you can go check out as well. But irrational numbers, let's look at the definition here. It says it's the set of all numbers that cannot be expressed as a ratio of integers. And when we think about ratio of integers, what we're basically saying is, if we think about it in fraction terms, what we could be saying is here is 3 over 4. Those are two integers. Okay, that makes it a rational number. Or negative 2 over 7. Those are two integers. The top is an integer, negative 2 is an integer, the bottom's an integer, 7. A rational number would be, it cannot be expressed as integers. You would have to use a decimal or another fraction involved. So it could be like 3.7 over 9. That's an irrational number, okay? But let me make that a little easier for you, okay? What do I mean by that? So a decimal, any decimal that is not repeating or let me read that again. Any decimal that is not repeating or non-terminating is an irrational number, okay? So I want you to think about irrational just being like, oh man, that guy's acting irrational. He's just like not himself. He's acting like out of his mind, okay? So that means it's a little bit crazy and it's hard to understand. But we think about rational makes sense. We're going to make sense of this thing. We can find something that makes sense. So that's what I want you to think of when you're thinking of the difference between rational and irrational. Let me explain that to you. And a rational decimal, so not the vocabulary word right here, but a rational decimal would be a decimal that stops, right? So if I was figuring something out and I found out the answer to be 7.94, that stops. That makes sense. A decimal that stops makes sense to us. That's rational. Or a decimal that can go on forever, but it's a pattern, so it repeats itself, like 4.9999. We see a pattern. Or negative 7.13, or 7.131313. It's a pattern. Patterns make sense to us. That's what we like about math. When you see a pattern, things start to make sense. An irrational decimal goes on forever, never stops, and has no pattern. Like pi, for example, 3.14, blah, 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 goes on forever. Okay? Anytime you're doing the square root, right here, the square root of a whole number that is not a perfect square, it's always going to be irrational. So if we were doing the square root of 25, which means something times something equals 25, that's going to be 5. But if we did the square root of 26, and we typed it in a calculator, it's going to be 5 point something, 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 goes on forever without stopping. That's irrational. That doesn't make any sense. Decimals that go on forever without stopping. That does not make sense. Okay, and another way to look at it is simply look at that last example that I gave you, which states that that decimal goes on forever. And the reason I know it goes on forever because you see those dots afterwards. If it goes dot, 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 that means there's no end in sight. If it was repeating, it would have a line over top of one of the numbers, which would tell us that this could be 0.2456366666666666. There's a pattern. That's rational. If it doesn't have a pattern, then it doesn't make sense. Okay, so those would be irrational. Okay, now let's look at radical expression as our next vocabulary word. Okay, next vocabulary word is radical expression, and it's any expression that contains a radical symbol. Okay. And this is a radical symbol. That's all it is. Okay, so like if we had 3 plus 7, that's an expression. But if we had the square root of 9, that's a radical expression because it's using this symbol. Make sense? That was pretty simple. Okay, let's go ahead and review what we know about square roots. All right, what does the square root of 16 mean? It means we're trying to find a number, because it's a square, that the side and the top, the two numbers are the same number that multiply together to equal 18. So that would be, what multiplies together to equal 16? That would be 4 times 4. So the answer to this one is 4. And then when you have it written like this one below, the opposite of the square root of 81, you're asking yourself, what number multiplies together to equal 81? Well, that's 9. 9 times 9 is 81. And when it has a negative in front of it, I always word it this way. What is the opposite of the square root of 81? Well, if the square root of 81 is 9, what's the opposite? Negative 9. That's how you would do those. Quick review. All right. So let's use rational approximation to the nearest hundredth to solve this one. Okay, so now this is not a perfect square. There's nothing you can multiply together that is an integer that will get you 44. All right, but we can get pretty close by figuring out which square roots are on both sides of this. Okay, which ones are on both sides. So then we can start narrowing it down on how to get closer to this. Okay, so if we did the square root of 44, what do we know? Like, what numbers multiply together to get close to that? Well, if you know your square numbers, you could say 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. And what I'm doing is I'm trying to get close to 44 without going over. So 4 times 4 is 16, 5 times 5 is 25, getting closer. 6 times 6 is 36, all right, getting closer. 7 times 7 is 49. So now we're too big. So we got the one that was before it, which was the square root of 36. And then we got the one after it, which was the square root of 49. So we know the answer to this one is somewhere between the answer to both of those. Okay, the answer to both of those. And so what we do is we can say that the square root of 36 is 6, and the square root of 49 is 7. So our answer is somewhere between 6 and 7. Okay, and we are... 44 is 8 away from 36, and 44 is 5 away from 49. So my guess is going to be that we are getting closer to 49. I'm sorry, closer to the 7 than we would be the 36. All right, so we know it's between 6 and 7. Let me clear my board, give myself some space. So we know it's somewhere between 6 and 7. And we're trying to get to the nearest hundredth. Okay? So we can do something like go and think about with your calculator. You could go and say, what is 6.5 times 6.5? Okay, so if we went to our calculator, and I'm going to use my friend over here, Alexa, and see what she knows. Alexa, what is 6.5 times 6.5? I'm using technology to my increase. That would be 42.25. Getting kind of close, aren't we? Okay, getting kind of close. So we could say we need to be bigger than that. So let's go back and try 6.7. Alexa, what is 6.7 times 6.7? 6.7 times 6.7 is 44.89. A little too big, right? A little too big. So now we're getting closer to the hundredths, right? Now we want to narrow this down to the hundredths. So I might say we're a little too big, so let's go back to 6.6. But we want to get close to the top there. So let's go 6.67. Alexa, what is 6.67 times 6.67? 6.67 times 6.67 is 44.4889. So now you know we're getting really, really close. Okay, we could probably go down to, Alexa, what is 6.62 times 6.62? 43.82. You see how we're getting closer and closer? Let's do one more just to try to get closer. Alexa, what is 6.65 times 6.65? 6.65 times 6.65 is 44.2225. So we are probably right around the 6.64 range to get closer. It doesn't need to be exact, because remember, this is going to be an irrational number. It's going to go on forever, but we're trying to get like a rational approximation of how close we can be. So the answer to this one, I would bet, is somewhere around 6.64, and I would feel pretty good about that answer. as being pretty accurate and pretty close to what we're trying to get to. So now we can kind of use that understanding to kind of think about where would these go. Okay, where would these go? So think about it. We want to find the perfect square on either side of these. And I can go and tell you that, I can go and tell you that none of these are perfect squares. Okay, but you guys have moved along far enough in your career, you hopefully understand what the perfect squares are. You have them sort of memorized. If not, you can get to them pretty quickly. But we just did one that was real close to the square root of 35, which we just said it was the square root of 36 is a square one, right? So that gets us at 6. And so the square root of 36 is the one past it. So that gives us 6. And what's the one before that? That would be the square root of 25, right? Because 5 squared is 25. So this square root of 35 is somewhere in between those two. Now, just using our understanding of square root of 35 is real close to the square root of 36. Well, what is the square root of 36? Well, it equals 6. So my guess is this guy right here is going to be real close to the 6. It's not going to be the 6, but it's going to be in between those two. Okay? Does that make sense? You try the next one. Okay? Square root of 106. What do we know about our perfect squares? Well, 106 is going to be a bigger number. It's not going to be 9 times 9 is 81. 10 times 10 is 100. And 11 times 11 is 121. So we're going to be dealing with the square root of 100 is the one below it. And the square root of 121 is the one above it. And the answers to those are 10 and 11. Now we just got to figure out where we're going to put that in between those two. Okay, well, 106 is closer to 100 than it is 101. So let's put it, it's in between 10 and 11. Let's go ahead and put it about right there. And let's do one more. Okay, this one's a little bit harder because it's bigger, right? Like we have a much bigger number. But one of those easy perfect squares is 20. And 20 times 20 is 400. So we know 400 is real close to it. So now we know we're dealing with 20 up here. And we're going to deal with the one right below it, which is 19. Okay, because 397 is real close to 400. So that's going to put us about right there. Okay, when I say put it right there, the square root of 397 is real close to the square root of 400. Okay, so we know it's closer to 20 than it is 19. And now where would these go on the line? The opposite of the square root of 54. So remember, you got 1, then you got 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. If you haven't memorized these yet, you should really memorize your perfect squares all the way up to 200, all the way up to 400. 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64. Okay? So those are our two radicals that are on either side of it, radical expressions. And this would be 7, and this would be 8, right? The square root of 49 is 7, square root of 64 is 8. But remember, we have this opposite, so we're dealing with -7 and -8. 54 is a little bit closer to 49 than it is 64, so it's going to be a little bit closer to -7. So that guy would probably go about right there. And the square root of 24, what two perfect squares are on either side of it? All right, well, square root of 3 is 9, square root of 4 is 16, square root of 5 is 25. That's a little bit too big, so we go back to the one before it. Okay, square root of 16 is 4, square root of 25 is 5. 24 is real close to 25, so it's going to be real close to the 5. Like real close. I almost put that on the 5, right next to it. Sweet, right? And now we're just going to think about how we can put these in order now that we understand how to use radical expressions. What does 3 squared equal? You know it, 9. What is the square root of 102? We can do that approximation thing to kind of figure this out. Okay. First of all, when we're looking at these, we can do all this math, or we could also just use our math understanding or our understanding of number sense. The smallest number is going to be the negative one. There's only one negative one in this answer right now. So this is going to be our smallest number. Okay. So that'll be the smallest. And then the next smallest, we have to figure these out. All right, so this is 9. The bottom one down here, 11, does equal 11. And 102 is going to be, the square root of 100 is 10. Square root of 102 is going to be something above it, like 10.12 or something like that. Now it's easy to figure out, right? What's the smallest number? The smallest number is our negative number. So this would be our smallest. What's our next smallest? 9. What's the next smallest? 10. And what's the next smallest? 4. Okay, those look like negatives. Let me put equals in front of them. Okay, so the smallest, and then they just get bigger and bigger and bigger. I think you guys are ready to crush this one. All right, thanks for coming and hanging out with us. Remember, when you're thinking about radical expressions, just remember if it has a negative sign in front of it, that means the opposite of whatever the value is. And when you have a radical expression that has a non-square number in it, okay, it's going to equal an irrational number. Irrational numbers make no sense. They're decimals that go on forever. Forever. Okay. You guys are amazing. Thanks for coming to hang out with me today. I think I already told you that one. What did the blackbird use to open the door? Crowbar. It's more of a hawk. Hope that didn't hurt your ears. You guys have a lovely day.